The first disaster involving a nuclear reactor in human history.
Calling this a reactor is being generous. It's time for some more plainly difficult. Specifically, the world's first nuclear reactor accident. Evidently, they did not see that one coming. For those of you who don't know me, I'm Tyler Folsom, a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I'm going to know everything there is nuclear, but I can certainly share some knowledge. Let's see.
It is July 1945, and all seems calm at Farm Hall, Godmanchester, England. Some new guests are at the house, and they are settling into what feels like a nice bit of English country luxury. The men, however, rather strangely for the time, being welcomed into the building, are German. And not just any Germans. They were, just a few years earlier, a vital part of the German war machine. So why are they in the relative luxury of their once enemy's countryside? Well, they are
the intelligence capture program to measure how far Germany got in nuclear physics at the time and whether the Allies were in danger of a German nuclear weapon.
Scientists, and they are prisoners of war. Clearly not all POWs after the fall of Germany in the Second World War were housed in such comfortable surroundings. They are to be interrogated by the British to try and find out what they had been up to during the past few years of the war. The men are known informally as the Uranium Club, and its lead was Werner Karl Heisenberg.
Now, Heisenberg was intellectually central, but there were actually multiple competing groups, not one unified command, which is one of the reasons why German nuclear work stalled during World War II. One of many, but every lab built its own prototype piles without collaboration or standardization, which would be unthinkable in modern nuclear engineering, and kind of surprised they even got as far as they did, which wasn't very far.
But we aren't here for a rundown of their 6-month interrogation at Farm Hall. We're actually here for a nuclear disaster.
This thing.
The first disaster involving a nuclear reactor in human history.
Calling this a reactor is being generous. But if he means reactor-like assembly, then sure. But this was not a criticality accident like the Demon Core or a lot of these early nuclear physics experiments. This was a thermochemical runaway, not a runaway chain reaction. So it wasn't due to a criticality issue or a reactivity excursion or power excursion like a lot of the rest of these early accidents were.
You see, the Uranium Club had been building a nuclear weapons program, and part of this was in...
Wonder if the Uranium Club was a term used by the British intelligence at the time.
A city called Leipzig. Today we're looking at the LV4 experiment disaster. My name is John, and welcome to Plainly Different, the German pursuit of nuclear. It's probably not a shock to anyone, but all of the major players in the 1930s were chasing the splitting of the atom, and Germany was no exception. This was unofficial.
Okay, yeah, I can understand, and hence the censoring in the initial title, why he's not going with the actual German flag in this time period.
Actually called the Uranium or Urane Project. Beginning not long after the discovery of nuclear fission in 1938 by Otto Franz Hitz-Strassmann, Lisa Meitner, and Otto Robert Thursch. The discovery would pave the way for nuclear power and atomic weapons. Happening just before the outbreak of the war, the discovery managed to make it to the United States. The German nuclear...
One of the key aspects of the uranium is that these first people to explain fission recognize that it released 200 MeV per fission, which is a key number that shows up in reactors today, and it's fundamental to predicting nuclear reactor behavior.
Efforts would quickly be stunted after the invasion of Poland, when men in the scientific community were pressed into service in the Wehrmacht.
Yes, there was loss of scientific personnel due to drafts, plus competing priorities. There was more scientific research into rocket technology within Germany at the time. And there was a belief that nuclear weapons were not feasible within the war's timeline. So Germany didn't really misunderstand the physics back then. They misunderstood the industrial requirement.
The drafted scientists were moved to a German army-led nuclear weapons program in the Heereswaffenamt. The Germans' weapons program was split into 3 sections: the uranium machine, or also known as nuclear reactor development, which is the main focus for our video today, materials production, i.e. uranium and vital heavy water, and uranium isotope separation. However, the project was slated to take at least 5 years before any usable weapon could be created, and because of this, in 1942, the project was very fragmented, with each department doing its own research to its own set of goals.
Another key weakness. So modern reactor development requires national laboratory level infrastructure. Germany had small university labs at the time with improvised materials, and they lacked some key ingredients, such as graphite of sufficient purity to be an effective moderator, and enough heavy water to attempt to sustain reaction. Mainly because enrichments, and this was all fairly cutting edge technology, either the materials and the infrastructure. So the idea of trying to enrich any uranium or even enrich water to make it into heavy water or getting high purity graphite, it just didn't exist back then because it had no other reason to exist. Because you would only need that in the context of nuclear technology. It didn't really exist back then.
And in relative isolation from one another. In order to research potential critical assemblies, 4 uranium machines would be tested at the Physics Institute in the University of Leipzig. They would be named L1 to L4 and were built to Heisenberg's theoretical work and tested by Robert Doppel. The test reactors were spherical, again following Heisenberg's theory. At one point...
So, I wouldn't go as far as to call these reactors. I'm okay with the term uranium machine, which was used back then, but these were subcritical assemblies, not reactors. They were designed to measure the neutron multiplication factor, or K-effective, which is a term that is still used today. And heavy water was the best moderator that was probably available to them at the time, and uranium oxide...
There was even another experimental pile at the University of Heidelberg. This was 4 tons of uranium oxide and 435 kilograms of water mixed in an earthenware vat.
So uranium oxide was used instead of metallic uranium due to shortages.
But that wasn't the only one. Another pile was also planned to be built in Berlin around 1940 and was designated the B pile. This was again a cylindrical shape, but was loaded with layers of uranium oxide, and interestingly having paraffin as its moderator. A chain reaction was not observed here, even when the uranium content was increased. Meanwhile, in Leipzig...
Yeah, they need better moderation.
Tests with the first 2 uranium machines, i.e. L1 and L2, were undertaken. These use uranium oxide and light water. On L1...
Light water, just standard water, H2O, with just the natural abundance of hydrogen 1, hydrogen 2, and hydrogen 3, meaning it's mostly hydrogen 1. Heavy water is enriched to being deuterium, or heavy hydrogen, which is more effective at slowing down neutrons to cause a fission reaction.
But 164 kilograms of heavy water was used in L2. L3 was assembled.
Oh, here we go. He even shows D2O, which is chemically the same as H2O, except a little heavier, but the deuterium is key in slowing down neutrons more. So, yeah, it's probably the best moderator that was available to them at the time.
By Doppel, and used 160 kilograms of heavy water and 140 kilograms of uranium oxide in 2 layers within a 75 centimeter aluminium sphere. And again, no increase.
Aluminum was chosen because it's easy to machine into things like a sphere compared to steel or lead, and because it's low neutron absorption, less likely to interfere with the fission reaction.
In neutrons was found, but the Leipzig team continued on. And this leads us on to the LV4.
So no neutron increase found. What he means by that is that does not mean the system was inert. It means K effective is less than 1, as in to say it's subcritical. So neutrons are going to die away faster than they multiply. They still multiply. It's called subcritical multiplication, and it can occur in a shutdown reactor. So multiplication still occurs, but it will not be self-sustaining. And in my opinion, if it's incapable of going critical, it's not a reactor. But it could eventually lead to the development of reactors. But in this design stage right here, they were subcritical assemblies. The whole point of this experiment was studying K-effective. And you can do that without having a critical reactor.
Don't worry, we are getting closer to a disaster. L4. The next part of the project was the L4, and it began in May 1942. The L4 pile used the same sphere principle style, with pure uranium powder weighing at 750 kilograms with 140 kilograms of heavy water.
Uranium powder is some spicy stuff, because uranium powder plus oxygen plus heat is pyrophoric. The material becomes self-heating, especially when packed in a confined vessel like that, because this thing isn't exactly a good example of ideal heat removal. Basically, they built a pressure cooker with pyrophoric fuel, so there's your risk.
These contents were placed within two aluminium hemispheres bolted together with a diameter of around 80 centimetres. The whole assembly was submerged in a bath of light water for neutron reflection and for a kind of biological shield. In the centre of the assembly was a neutron
Water is a good shield against radiation.
source injection channel, in which a beryllium starter source would be inserted. At the top of the reactor vessel, there was a vacuum. This allowed for thermal expansion of the heavy water. But those of you who have seen nuclear...
Alright, so this is probably the most hazardous design feature here, because that's a chemical hazard, because air is going to rush in when that vessel is open. And today, uranium powder is stored in an inert gas or vacuum and is never opened without establishing a nitrogen blanket to prevent it from interacting with air.
Reactor-based videos on the channel before might have noticed something a little bit absent. That is any form of radioactivity control, if a chain reaction were ever to take place.
So that's true, no control rods, but this isn't a reactor. A chain reaction could not occur. It could not go critical with the materials they had. But yeah, that's true and definitely weird that they didn't have any reactor trip function, no absorption injection system, and yes, modern reactors have control rods, neutron absorbers such as boric acid, shutdown margins, which this thing did have, but I don't know how robust their calculations were, or if it had a requirement of how much the vessel is shut down. And what shutdown margin means is how far away you are from criticality. That is to say, you have so much more control rod equivalents such as boric acid or some other form of neutron absorber, such that if there was a way to add positive reactivity somehow, you're still going to be shut down by a sufficient margin. There's also no passive safety. Again, I know this was a physics experiment and not a reactor, but with modern radiation protection, I get where he's coming from of having a thing that bakes neutrons that has subcritical multiplication without any form of reactivity control. A spent fuel pool is analogous to this because it's not a reactor. You can't take it critical. However, it is borated with a sufficient concentration of boric acid in order to maintain that shutdown margin. So it is impossible, even if you were to add reactivity somehow, such as, say, diluting boric acid or something, then it still has a sufficient margin that it would not go critical.
Thus, there was no real way to shut down the pile if it got started. During the 20 or so days that the L4 was active, the scientists noticed that the pile was beginning to emit more neutrons at the pile's surface than just what the source itself would have emitted.
And this isn't like a power meter, it would be, you look at neutron detectors. They would tell you this information.
It looked like the pile was starting to work. However, scientists working on the pile saw bubbling water at the top seal, and this was hinting at a potential leak. This was June the 23rd of 1945. Operators were ordered to open up the pile, bearing in mind that the reactor had no criticality controls. When the pile was opened up, air was sucked in from the...
So before they do this, all right, so bubbles at the surface, possibly the neutron multiplication factor could have upticked a little bit, showing neutron moderation and reflection increases, but it was still nowhere near criticality. However, any unexplained increase in counts on a sealed heavy water sphere with uranium powder in it should have been seen as a red flag. But them opening this, man,
vacuum
no.
at the top of the pile. The air, most notably the oxygen in the air, reacted with the hydrated uranium powder. Quickly, the mixture ignited, and temperatures within the pile sped up to nearly 1,000 degrees centigrade.
Okay, so opening the pile, the defining mistake. Opening a sealed, potentially heated, oxygen-sensitive uranium system. You might as well be opening a glowing charcoal grill full of magnesium dust. If you suspect heat, pressurization, or reactivity, you need to treat the vessel as live until proven otherwise. But yeah, 1000 C, yep, once uranium dust ignites, the reaction is very self-sustaining and extremely hot. Kind of like a thermite reaction. Now, we're talking chemical reaction here. We're not talking fission or prompt criticality or anything like that. Now, that doesn't mean there's not a radiological hazard, because it can come from this uranium oxide aerosolizing. Yeah, you get something that's radioactive and it can contaminate the air. It can contaminate the water. And it can lead to a loss of inventory of the water, because the water is an effective shield, whether it's heavy water or light water, as far as radiation is concerned.
This ended up boiling the water inside the sphere and the light water reflector. A massive self-deconstruction of the pile followed, shooting boiling water and...
Self-deconstruction, that is perfect post-event report, root cause analysis, engineering term. Well done. The word explosion isn't used very often. It's things like self-deconstruction, thermal event, thermal runaway, reactivity transient, things like that.
Burning uranium powder up into the air by several meters. Multiple smaller explosions and fires would continue on for 2 more days after the accident, in doing so destroying the building and the pile that was situated within it.
So, a steam flashover combined with uranium oxidation, or a pressure cooker bursting while filled with molten metal and corrosive steam. So, yeah, a chemical accident.
Human cost is very vague. Reportedly, no one was killed by the accident, although some other reports have had the death toll up to 4. One thing that is certain, though, is that the event probably caused longer-term conditions from the exposure. Although,
sure, yeah, likely something like this. Probably no immediate fatalities, but it's probably going to be some long-term radiation exposure, considering these guys were standing right next to the whole thing. Definitely major material loss, because heavy water was extremely scarce back then.
Tracking this is next to impossible due to the historical period. But the damage to the German weapons program was much further reaching.
I mean, it's 1945 at this point. That war is pretty much over. Can argue the turning point had already passed a while before then.
The aftermath. Now, the explosion was not just the loss of the pile, but the loss of the very valuable uranium and just as vital heavy water. It would set back the disjointed program. The pile experiments at Leipzig were cancelled. Instead, further pile experiments would take place at the Berlin campus. But although a catastrophic, unexpected uranium conflagration, the L4 had proved that net neutron production could be achieved in the German project.
Yeah, though they kind of already knew that even back then. Heisenberg's theory and earlier subcritical assemblies have demonstrated that proof of concept. What this did prove was they still lacked the proper materials for criticality. Oh, and they had a bunch of holes in their experimental safety procedures and processes and engineering.
The efforts in Berlin would be continued to be wasted by the German war to turn against it. Another experimental pile, the Hagelot research reactor, did achieve a chain reaction from neutron bombardment of uranium, but it did not achieve criticality. This happened just...
Again, subcritical multiplication. L4 and none of these other experiments were anywhere close to critical. None of these were.
In the closing days of World War II, the German nuclear reactor program would abruptly end when US soldiers ended up turning up and deconstructed and shipped off the reactor to the USA for investigations towards the end of April 1945. Now this leads us back to Farm Hall in England between the 1st of May and 30th of June 1945. Many of the higher up ranking scientists of the German nuclear program had been captured. 10 were transferred to the UK for interrogations. During this time, the world's first nuclear reactor disaster came to light, as the scientists were bugged at Farm Hall and their conversations were overheard. Interestingly, they were very ignorant to the US nuclear program, as when they were told of the more successful deployment of atomic weapons over Japan, many showed complete disbelief. They were...
Yeah, their estimates were off because they assumed bomb-grade uranium would require tons of isotope separation rather than mere kilograms. And they grossly underestimated the feasibility of large-scale industrial enrichment. So, yeah, these guys would be surprised.
A long way off building a nuclear weapon. But at least they did get one first in nuclear history, and although this would not, as we all know, be the last nuclear reactor accident to ever occur.
Again, I wouldn't go as far as calling these a reactor.
So that's my video on the world's first nuclear reactor disaster. I know I'm no Mark Felton, but my rating is going to be a 1 on the disaster scale, and this is what I've got for my root cause analysis card.
Alright, let's see. Easily preventable, time pressure, overly confident, complex system, recently inspected. I would add no training, and that's because they didn't really know what they lacked every safety system required for criticality experiments. And I would say this is a case study of what happens when physicists attempt to build reactors without nuclear engineers. Thanks so much for the recommendation, and thanks so much for watching. I'll see you next time.